Alright, we're going to pick up where we left off yesterday with valence shell electron pair repulsion theory. Valence shell electron pair repulsion theory. This theory is what again allows us to predict the geometries based on Lewis structures, and the last one we were looking at yesterday was something like phosphorus pentachloride. So again, the first thing you need to be able to do is to write the correct Lewis structure for phosphorus pentachloride. So we look at the number of valence electrons. It's 5 for phosphorus, and we have 5 chlorines, and there's 7 valence electrons for each chlorine. So if we add this all up, we get 40. So phosphorus goes in the middle. It's the has the least electronegativity, and then you can put the 5 chlorines around the phosphorus any way you like. Alright, we know there's at least one bond between the phosphorus and chlorine, so that they're bonded together, and we know that each chlorine has to have 8 electrons around it. So these 3 lone pairs, or 3 non-bonding pairs that we're putting on each chlorine, give each chlorine 8 electrons. So 8 times 5, there's 5 chlorines, there's 8 electrons around each chlorine, so 8 times 5 is 40. So this is the correct Lewis structure for phosphorus pentachloride. It does not follow the octet rule. It follows the expanded octet, because if you've got 5 things bonded, that means there are 10 electrons around the phosphorus. So once you get the Lewis structure, the next thing you want to do is evaluate the electronegativity difference between the phosphorus and the chlorine. So phosphorus is less electronegative than chlorine, so the phosphorus gets a partially positive, chlorines get a partially negative. So these are delta, lowercase delta negatives. Or if you like, you can draw arrows pointing towards the more electronegative element, like so, the positive end on the phosphorus. So that's the Lewis structure part. Now, Chapter 10, the valence shell electron pair repulsion theory. What we do from the Lewis structure is we first come up with the classification. The classification, A stands for the central atom, X stands for the number of bonds coming off the central atom. In this case there are 5, so this is an AX5 classification. So that's what we call this, classification. To me, this is the most crucial step, because it allows you to start thinking about what the geometry should look like. So the question is, if I have 5 things attached to the central atom, how are those arranged in 3-dimensional space so that everything feels like everything is as far away from each other as possible? Well, for phosphorus pentachloride, that geometry is going to look like this. Phosphorus in the middle, chlorine here, and a chlorine here. And then there's a chlorine here. There's one that's in the same plane coming out of the screen at you, and there's one going back behind the screen, signified by the dashed line. Now remember that these chlorines are called equatorial chlorines. These are on the equator, and this chlorine and this chlorine is called the axial chlorines because it's in line with the phosphorus here. So this geometry is called trigonal bipyramidal. Oops. Bipyramidal. Now, if we look at the electronegativities, these are polar covalent bonds, which that's half of the equation to get a polar molecule, a molecule that has a positive and negative end. But the problem is this force is equal and opposite this force, so they cancel each other out. And we've already seen that in a trigonal planar type framework that we see here in the equator, those cancel each other out. Or if you like, if you make these all partially negative, the chlorines, and the phosphorus partially positive, there's no way you can draw an imaginary line through this molecule and get a positive end and a negative end, which means a dipole moment. So there's no dipole moment in this molecule. and therefore we would have this molecule would be nonpolar. All right. Oops, let's go on. Okay. Next Lewis structure, sulfur tetrafluoride. All right. So 6 valence electrons for sulfur, 4 times 7 for the fluorine. We're dealing with a 34 electron system. Sulfur goes in the middle, and we'll put the 4 fluorines like so around the sulfur. We know that each sulfur has one bond to this fluorine, so we put one single bond to each fluorine. Alright, so 8 times 4 is 32, but we got to have 34 electrons. Now here's something crucial to remember. If everything is satisfied with 8 and you have extra electrons, I mean we've accounted for 32, but we're supposed to have 34. Any extra electrons always go on the central atom. So that's what these 2 dots here represent. 2 electrons that's been assigned to the sulfur, and now that gives sulfur a total of 10 electrons, but that's okay because remember sulfur can have an expanded octet. So this is the correct Lewis structure for sulfur tetrafluoride. Next, you would want to evaluate the electronegativity differences. So we know that fluorine's more electronegative than sulfur. We definitely have polar covalent bonds. That's half of the equation in figuring out whether we have a polar molecule or not. Now the next half is to come up with the classification and geometry for this structure. Alright, so the classification for this is AX4E. It is 5 things still coming off the central atom. It's 4 bonding pairs and 1 non-bonding pair. Here's the non-bonding pair here. Okay, so the sulfur goes in the middle, fluorine in the axial position, fluorine in the axial position, and a fluorine in the equatorial position, and another fluorine in the equatorial position, and then maybe going back through here is the non-bonding pair, so you make a balloon here like that. Alright, so we know that the fluorines are partially negative. We know that this force cancels this force out. But this force is not canceled out here because there's no fluorine in the non-bonding pair here. So this molecule is polar. It's a polar molecule. The shape or the geometry of this molecule is called seesaw. That's the old name for it. Or distorted tetrahedron. One of the things we need to know is what is the angle between the fluorine axial, the sulfur, the fluorine axial. So we're talking about the angle between here and here. Well, you would say less than 180 degrees. All right. What is the angle between the fluorine equatorial, the sulfur, and the fluorine equatorial? So we're talking about the angle between these 2 fluorines. You would say less than 120 degrees. And the reason why these are both less than is because you have this non-bonding pair that forces the bonding pair closer together. In fact, another way to draw this is sometimes like this is actually a better way. You draw these fluorines in the axial position kind of bent back like so, and the fluorine here, and then you've got the fluorine kind of coming out, it's bent back too, and then the non-bonding pair out like this. That's how they get the distorted tetrahedron. Also, you can kind of, let me move this just a little bit to accentuate it a little bit more. You can say these are all partially negative, and the sulfur is partially positive. You can draw an imaginary line through here. It's strictly positive on this side and strictly negative on this side. So that's another way of determining the polarity of the molecule. So whether you do it by vector analysis or by the line method, everything on one side positive, everything on the other side negative, you'll come up with the same conclusion that the molecule is polar. Now, going back, I want to go back to the last slide because we didn't talk about the angles here. Again, the angle between a chlorine equatorial, the phosphorus, and a chlorine equatorial is 120 degrees. Like that would be these angles, 120. We've already seen that. Trigonal planar, that's what this is, right? This is all in a plane at the equator, 120 degrees. Now, between the angle between chlorine axial, phosphorus, and chlorine axial would be 180 degrees. That would be from here to here. And then the last angle would be chlorine axial, phosphorus, chlorine equatorial, which would be 90 degrees. So these are the angles that make up the trigonal bipyramidal framework. All right, let's continue on. So the next example would be something like ICl3. So let's look at that one. We've got 7 electrons for that, 3 times 7 for this. That's a total of 28. So the iodine goes in the middle. We put the chlorines around it like so. So we know there's at least one bond with each one of these. And we know each chlorine has to have 8. Alright, so 8 times 3 gives us 24. But we've got 28 electrons. So we're going to have 2 lone pairs on the iodine like so. Remember, the excessive electrons always go on the central atom. Okay? So iodine has 2, 4, 6, 8, 10 around it. It's okay because it can have the expanded octet. Chlorine is more electronegative than iodine, so partially negatives on the chlorines, or if you like, the arrows pointing towards the chlorines. Alright, so there's our Lewis structure. Now, as far as the geometry goes, we got to get the classification. It's AX3E2. 2 non-bonding pairs and 3 bonding pairs. So it's still 5 things coming off the central atom. The framework is still trigonal bipyramidal, but it would look like this. Iodine here, chlorine in the axial position here, chlorine in the axial position here, chlorine in the axial position here. But now we have 2 lone pairs, and both lone pairs always go in the equatorial position when we're dealing with this geometry. Always in the equatorial position. And the reason why is because there's a lot less interaction. If I put this lone pair in the axial position, I would have a 90-degree interaction with these elements or these electrons in the equatorial position. So that's more interaction, more repulsion. So that's why the non-bonding electrons always go in the equatorial position. So again, I'm not drawing this the best because in reality these chlorines are blown backwards like this, right? You got 2 lone pairs now. It's really forcing this back like that. All right. And so these are partially negative. This is partially positive. You can draw an imaginary line. It's definitely a polar molecule. Or if you do the vector analysis, nothing's canceling out that vector. And these are, even though they're not 180 degrees because they're blown back, the overall direction, the resultant force is somewhere in that direction like that. So this is a polar molecule. The geometry is considered T-shape. T-shape. Before these are blown back, it makes it, and it still looks like a T. Here's one part, here's the other part, and there's the other part. T-shape. So